do one more review. Quick review. All right, so our focus was
we crash it. We don't care about the damage. We care about the people. Our testing exceeds the government standards. Ford has more 5-star rated vehicles than any other car manufacturer. We go that extra mile to make sure that our cars are safe. I'm proud of that. We don't care about the damage. We care about the people. We don't care about the damage. We care about. We don't care about the damage. We care about the people. We don't care about the damage.
I mean, look at the damage. 40 miles per hour, and this car is totaled. Why did they make these cars so fragile? The reason is because of safety. So my question was, why not make the outside of the car indestructible and put the safety on the inside? Why not do it that way? And furthermore, crushable cars. Being able to crush a car, why does it make it safer? Safety is the issue because acceleration can kill. Acceleration is what kills you, what maims you, what breaks your bones. In fact, the prolonged exposure to 7 Gs or more acceleration. So the question is, how does acceleration kill? So if you're exposed to 7 Gs, 8, 9, 10, 11, 12 Gs up to 15 minutes, potentially it can kill you. So how does acceleration kill? So when you're inside the car, when the car speeds up, accelerates in the forward direction, what happens to your body? You feel a push in the opposite direction of the car, right? And then you put the brakes on. Now you will go forward direction. You will notice that your body always moves in the opposite direction of the acceleration of the vehicle. Because the unstrapped object on the inside will always move in the opposite direction of the acceleration of the vehicle. If I'm driving my superpower tempo in this direction at 7 Gs, what happens to my body? I will feel a push at 7 Gs in the opposite direction of the motion of the vehicle. That's fine. What happens to the blood in my body? It's going to get pushed to the back of my body. What happens to the blood in my head? Once again, the same thing. It gets pushed towards the back of my brain. What happens to the frontal lobes? Lack of blood, lack of oxygen. Eventually, I will pass out. If you keep me there long enough, it may kill me. It may end up killing me, in essence. All right, except pilots, when they're being trained inside a centrifuge. They're not speeding up or slowing down. They're moving at a constant speed while experiencing 7 Gs of acceleration. So how do we induce acceleration at constant speed? Which means that we have to add on to what we consider acceleration. Pendulum is going to move backwards when the current is forward, so the unstrapped object still moves in the opposite direction of the acceleration. It's going to move forward when the acceleration is backward. So what happens to this pendulum while you're actually driving in a circle? Instead, it once again moves in the opposite direction of the acceleration. Given the fact that it moves away from the center of a circle, this implies that the acceleration is going to be directed to the center. That's it. So circular motion at constant speed, you're still accelerating because your direction keeps changing. So how fast you speed up is acceleration. How fast you slow down. Also, how fast you change direction is acceleration. So now we're building up our definition. So speeding up is acceleration, slowing down is acceleration, and changing direction is also acceleration. Combination of speed and direction is known as velocity. So the summary statement is how fast the velocity changes in time. Acceleration is expressed in terms of meters per second squared, so that's the proper unit. And for safety reasons and safety reasons only, we like to express that in terms of Gs. So 1 G is your own body weight. It feels like your own body weight. 7 Gs is going to feel like you're 7 times heavier. 12 Gs feels like you're 12 times heavier. All right, so acceleration is speeding up, slowing down, and changing direction. It's a vector, guys, which means it's got direction. It always points from a smaller to larger velocity. In this case, you're speeding up. All right, because you're speeding up, this is known as positive acceleration. So the positive acceleration simply means speeding up. If you're slowing down, it's known as negative acceleration. Your initial velocity is larger than your final velocity. So the vector is going to point towards the larger of the two velocities. In this case, it's pointing towards the left. So if the acceleration value is negative, we will take that to mean you're slowing down. Positive means you're speeding up. Negative means you're slowing down. We'll look at John Stapp experiment. Let's see if this works. Okay, so let's go back to the original page.
In the 1950s, years before the Pinto or Corvair, little was known about the essence of a collision, how much force the driver could withstand. To find out, a seemingly lunatic experiment was carried out in the New Mexico desert by the U.S. Air Force in 1954. Scientist John Stapp strapped himself onto a rocket sled to boldly go where no man had gone before.
He started the countdown.
10, 9.
Adrenaline comes in and the heart begins to beat a little faster. Then just as he reaches 0, you get this enormous ram against your back and feel totally helpless. You're given the biggest kick that could be delivered.
Stapp had been propelled at a speed of 632 miles per hour and stopped in 1.4 seconds. No one has ever undergone such a test before or since.
I couldn't see anything, and I was looking around, and I was beginning to think about seeing eye dogs and white canes. And I was thinking to myself, now I've paid my dues. I've gotten there. I've shown them what they want to know. And from now on, life is going to...
All right, so it was brought to a stop from 632 miles per hour to 0 within 1.4 seconds. And he was exposed to about 20 Gs. It's negative, meaning that he was slowing down. So he was exposed to 20 Gs, and what happened to him? His breathless got there. And that was the extent of the damage. He survived. So we got what we were looking for. What we were looking for was, what is it that you could be exposed to and still be able to survive during our car collision? So 20 to 25 Gs is what we're at. So you should be able to survive up to 20 to 25 Gs for a few seconds. All right, because he was able to survive 20 Gs for up to 1.4 seconds, which means that it should be very easily survivable.
The Mercedes S-Class is one of the biggest and strongest cars in the world. It's also one of the safest. But in Paris, on August 31st, 1997, this car was involved in the most notorious car crash of all time. The Mercedes was carrying 4 passengers, a chauffeur, a bodyguard, the Princess of Wales, and her boyfriend. They were reportedly speeding away from photographers when their car approached a narrow underpass. Professor Murray Mackay is Britain's leading car crash investigator. Using official reports from the French police investigation, he's reconstructed what happened.
According to the accident investigators, this is where the accident began.
About 20 past midnight, the Mercedes is coming along this road on the left bank of the Seine towards the Alma Bridge. It heads down towards the underpass, and it's estimated at that time it speeds about 70 miles an hour. What happens next is based on the evidence that we have so far. As he comes down into the tunnel, he's faced with a slow-moving Fiat. He steers to the left. Because he's just come over a crest, the steering's light, he probably puts in too much steering, so he's heading towards the center of Poland. He corrects right, and now he's heading directly for the Fiat Uno.
According to police reports, the Mercedes sideswiped the Fiat, but the only damage so far was a broken mirror and a smashed taillight.
Was the Fiat just an innocent motorist returning late at night, or was there something more sinister than that? We may never know. The French police have given up the search for that vehicle. What we do know is that at this time in the accident sequence, the actions of the driver of the Mercedes were not those of somebody who was normal and alert.
A 106-foot skid mark shows the Mercedes driver pulled the steering wheel back to the left. The car jumped the pavement and smashed head-on into column 13. The car spun around and ended up facing in the direction it had come from. Mackay thinks the Fiat drove by without stopping.
Speed, a driver under the influence of alcohol, the unexpected encounter with the Fiat, these all played their part. But you must remember that from the time the car entered the tunnel until it came to rest after the impact, that's only about 2 seconds. Newspapers have talked luridly of speeds of 120 miles an hour, but looking at the damage tells a very different story. It suggests an impact with the pillar of about 60 miles an hour. And we know that the car came to rest about 15 feet from the pillar, spinning out, and that means about 10 miles an hour exit speed from the pillar. So the change in velocity was slightly less than 50 miles an hour. And it's that change in velocity which is crucial in terms of the severity of the crash to which the occupants were exposed. This was a severe but a survivable accident, and what we now need to consider is why did 3 people...
All right, let's get back to the statement that he's making. He says that this was a severe but a survivable accident.
Act with the pillar or into the tunnel until it came to rest.
Imagine that you see this car on the side of the
Rest after the impact. That's only about 2 seconds. Newspapers have talked luridly of speeds of 120 miles an hour. We know that the car...
You see a car like it's on the side of the road. Are you thinking to yourself that this is survivable? Yes or no? Do you expect to see anyone surviving something like that? What's your first impression?
I would think they're dead.
Yeah, Kalmar, I'm going to give you 2 points for that one. Yeah, I mean, if you're driving by, I'm not thinking that anyone is going to survive this. In fact, if there are any survivors, I would go, wow, that's a miracle. That's the way I would think, or I would have thought if I were not a physicist. because I'm a physicist, if I'm driving by, this is exactly what I want to see. It's a bad accident. Car should take the brunt of the impact. The car should crumple. The car is built to crumple in order to make this survivable. What's surprising is not so much that this is survivable. What's so surprising is the fact that you have 4 people in this car. 3 of them are dead. And there's only 1 survivor. And the survivor is the guy who barely survived. He was in a coma for almost 2 weeks. How's that possible? According to physics, this should be survivable. According to physics, this should be 100% survivable. Yeah, something went terribly wrong. The question is, what? The first thing we need to look at is, why do we think that this should be survivable? Obviously, the guy happens to be an expert. He says this should be survivable. I'm a physicist. I'm looking at it. I say this should be survivable. Yet the facts are you got 3 people dead.
After the impact.
So what went wrong? Let's get back and take a look at the numbers. Here's the reason why we think they should be 100% survivable.
2 seconds.
So it takes 2 seconds to get to the 13 point.
Newspapers have talked luridly of speeds of 120 miles an hour, but looking at the damage tells a very different story. It suggests an impact with the pillar of about 60 miles an hour.
So that's your initial velocity, 60 miles per hour.
And we know that the car came to rest about 15 feet from the pillar, spinning out, and that means about 10 miles an hour.
So the final velocity is 10 miles per hour. What is the change in velocity under the circumstances? It's 50 miles per hour. Like, that's crash test. That's a crash test in speed, 40 to 50 miles per hour. Cars are crash tested at 40 to 50 miles per hour. So change in velocity, in this case, is 50 miles per hour. The only thing we need is the impact.
Exit speed from the...
Where do you suppose we get the impact time from? Let me show you where you get the impact time from. This is known as a crumple zone. You get the impact time from the crumple zone of the car. Engine compartment is your crumple zone. At 40 to 50 miles per hour, you should get at least 1/10 of a second from your crumple zone. So where do you get your impact time from? You get it from your crumple zone. The cars are built to crumple, to give you that impact time. So at the very least, you can survive something like this at the risk of losing your car. So your impact time is going to be 1/10 of a second in the worst case scenario. In the worst case scenario, where do you get your impact time from? You get your impact time from the crumple zone. The car is going to crumple. It's got a crumple zone. Engine compartment is a crumple zone. All right, so with that impact time in place, which is 1/10 of a second, your change in velocity is 50 miles per hour. Then what happens? All right, so your initial velocity is going to be 60, final velocity is going to be 10 within 1/10 of a second. You got 22 G's. It's negative, which means that you experience 22 G's of acceleration as you are slowing down within 1/10 of a second. 22 G's. Question is that survivable and why? What do you guys think? Can you survive up to 22 G's for 1/10 of a second? Yes or no?
I think yes, because I believe you could survive up to 25 G's.
Okay. Well, listen, I'm going to give you 5 points. The only thing I don't like about what you just said, don't say I believe. Because when you're talking about a belief, that's an emotional commitment to an idea, whether it's right or wrong. You know that for a fact, right? You know that you can survive up to 20 to 25 G's. How do we know that?
You know that from yesterday's lecture.
Yeah, I mean, as well as the review, right? We know that because John's staff was able to survive. Comparable numbers, up to 1.4 seconds. Up to 1.4 seconds. He was exposed to the same degree of acceleration for a duration which is 14 times longer than 14 times longer. Whatever the hell these people went through. John's staff experienced the same thing for a duration which is 14 times longer. And his retino's got detached. That's it. And then he recovered from it. And these people, 3 of them, while they were being exposed to the same sort of acceleration for a duration which is much, much shorter, some that they all should have survived, instead these 3 out of 4 end up having a permanent out-of-body experience. What went wrong? This is survivable. This is survivable. This is I don't want to say this is a piece of cake, but this is survivable.
Strangely, Princess Diana, sitting where I am in the right rear, had the best chance of survival because the impact was concentrated on the left front of the car, and as it hit the pillar, it also rotated and span out, so she went partly past the pillar and didn't have quite the same crash forces applied to her as happened to the people sitting on the left. If she'd been wearing a seatbelt, she'd have had a fair chance of surviving even this extreme accident. But unbelted, she was thrown forward to strike the back of the front passenger seat, the door pillar, and then was tossed around after the main accident took place and the vehicle span out.
Oh, she wasn't wearing a seatbelt?
Strangely, she'd have had if she, as happened to the people sitting on the left, if she'd been wearing a seatbelt, she'd have had a fair chance of